Okay, welcome back to this class where we are discussing the application of your DTA technique, and we know that there are several such applications, and particularly the most important one is the use of this DTA instrument in pharmaceutical industry. So, in pharmaceutical industry, this particular technique along with the next technique what I will be talking about, the DSC, is widely used for the typical analysis of the drug, the medicine, the tablets, the capsules and all. And similarly, the DTA can also be very much useful in the food industries, where the food industries can analyze the purity of the sample and its thermal stability of the sample, and if we add something more to that particular food, it can also be detected very nicely by using this particular technique. So, it can also be very much useful why the inorganic people, the inorganic chemistry people are also interested to study this DTA, because the DTA can be very much useful for cement industry. Similarly, the geologists also use DTA for their mineralogical research, and the last one is very important, that the environmental studies, because we have seen that the amount of gas what is coming out and how we can burn the gas in different atmosphere, that is the most important topic in terms of your air pollution and the environmental studies. So, to study environment nicely in terms of the quality of the air and the other environments like your carbon dioxide environment or the nitrogen environment, if we talk in terms of whether it is contaminated with some other gas molecules, that can be studied by your DTA. And it can be very much useful for archaeological studies also. So, it can be used to use the date, that in the dating we know that the radioactive dating we know, and the bone remains, because the bone, the remaining bone part of the living organisms or in the simple dinosaurs and all. So, the bone remains can be analyzed initially by this particular technique to study the archaeological materials what we basically unearth from the earth surface, and down the earth surface also we find some unknown material. So, if any unknown material in your hand, we can always use two important technique. One is your IR instrument, use of IR instrument for IR spectroscopic study, and then we can use the corresponding TG and the DTA plot for all these studies. So, next we will move to differential, another differential technique, so which is differential scanning calorimetric technique, which we consider it as a calorimetric DTA study. So, it is calorimetric DTA study, because this DTA, what we know that a conventional one, we indicate the corresponding temperature where the corresponding heat effect is we can see, but the corresponding sign and the amount of that particular magnitude of that particular change we cannot monitor. So, if we go for that, a qualitative analysis is not very useful. So, it is impossible to obtain sometime the quantitative data. So, how we get the quantitative data out of this particular technique? It is sometimes very difficult to get it from your DTA technique. We should go for the corresponding DSC, where we can locate the corresponding heat of transition. If the sample what we use is a pure one, so if the purity of the sample, if the purity of the sample is known, we can find very nicely the heat of transition. So, then we can find if the sample purity is related, then the amount of that particular constituent, we can find. So, all these things which was not very much controlled in case of DTA, we can monitor it for taking this particular furnace to a calorimeter. So, we can have a good control regarding the corresponding furnace, that we know that amount of heat we can put or amount of heat which can come out. So, is a thermoanalytical technique in which the difference in the amount of heat, now we are talking not in terms of the corresponding temperature difference, but we are now talking in terms of the corresponding amount of heat required to increase the temperature of a sample, and the reference is measured as a function of temperature. So, either the function of the temperature in terms of the temperature of the furnace or the temperature of the sample. So, we have a controlled temperature program, and that controlled temperature program, you can have a sample compartment what we can have earlier in case of your DTA apparatus, and that sample compartment can now be converted to a differential calorimeter. So, if you have a differential scanning calorimeter in hand, within which you put both R and S, the reference material and the sample material, and if the differential scanning calorimeter is of isothermal type, and we have a corresponding resistive heater in your hand, and the thermocouples are also connected which can register a voltage, and you can have the automatic control loop, and that control loop it can goes through the Wheatstone bridge, and that gives rise to the corresponding recording of the system. So, the sample holder temperature increases linearly as a function of time, as we all know when we heat the thing, and the reference sample should have a well defined heat capacity. So, these are the two things that we can monitor within this particular thing. So, as we have seen just now that you have R within a cavity and S also within a cavity. So, if everything is now enclosed, so this is the corresponding furnace, and that furnace can have the corresponding heating capacity for heating both the two things together. So, this is the most important and useful one, is the corresponding chamber for that, and this is the typical instrument, how the instrument look like, the DSC instrument. So, this DSC instrument in our hand, where we have the change the differential of the corresponding energy to heat the sample or the reference, because these two sample and the reference we want to keep the two temperatures within equality. So, very close. So, if you have the reference as we seen just now and the sample, so we have R and S, and we want to keep them to a very small temperature difference or the amount of power required, because one can be cold and another can be heated up. So, the two temperatures should be kept very close to is equality. Then some connectivity we have, that you have the recorder. So, the recorder will record the corresponding thing, that means the corresponding one, that how it can trace the corresponding plot, and ultimately the plot you can have. So, this thing that the instrument is, and this scanning calorimetry what we can use it for so many things. So, is a big list, but if we see one by one, so it has the same temperature effect or the thermal effect, because you have the reference and the sample. So, one is known, the reference material and the reference sample is known. So, if we have this thing, that means the thermogram we get which resembles that of your DTA, but the area under the peak now, area under the peak for DSC measurements will be equivalent to the amount of energy supplied either to the sample or to the reference. So, the supplied amount of energy, it can be either absorbed or emitted. So, the position in the chart which indicate the temperature at which the transition is taking place, but we can have the corresponding energy compensation in terms of the energy what we can put to the reference or to the sample. So, we have the reference which is known and the sample which is unknown. This is our reference material. So, if we put energy to the unknown only, that means energy is being supplied to the unknown sample what we are monitoring. So, why? Because if it is only the corresponding endothermic process, to compensate, that means we have to keep these two temperature very close by. So, energy should be supplied to your sample to compensate any endothermal event, to compensate any endothermal event. So, similarly, energy will be supplied to the reference material, because the reference material, if it is exothermic, the temperature of the sample will be up, reference will lag behind. So, in that case energy will be supplied to the chamber where you have an exothermal event. So, these two events, whether you have exothermal event or the endothermal event, can be monitored very nicely for large number of reactions which are triggered by a change in the temperature of the medium which we keep in the furnace. So, most interesting thing is the solid state analysis. So, solid state material, any powder to polymer to rubber can be analyzed very easily, and we can study those things for their melting and crystallization behavior. So, this melting and crystallization behavior is very important, because we can see the corresponding melting is a transition process where solid is going to the liquid or the molten state. So, we record that things, that means the corresponding transition temperature can be recorded, and if it is high, that means it has the solid state and the crystalline form has good stability. So, the crystallization behavior can also be monitored if we cool down the system and we look at the recrystallization. Then some solid state reactions we can see. So, the DSC trace for a particular type of solid state reaction, whether that particular solid state reaction, we all know that you can go for a simple metal complex preparation. One good example is well known, that the preparation of Reineke salt. So, the preparation of Reineke salt can be done by using simple solid-solid reactions. So, on sand bath we do some solid component with the other solid component, but the ultimate product is a well known different type of metal complex. Then polymorphism, as we have seen in case of DTA analysis, that the polymorphism for the pharmaceutical industry will be very useful. Then the degree of crystallinity. So, the degree of crystallinity of the crystalline samples, the TG we can measure, that means the glass transition temperatures for the polymer material or the rubber material we can measure. Then any cross linking reaction. So, if we hit the polymer and if we study the polymer by DSC technique, what we see that these cross linking reactions can take place. Sometimes we add sulfur for vulcanization also, and sulfur can also be useful for the cross linking processes. So, this particular reaction, if we minutely see the corresponding heat effect and the energy change for that cross linking reactions, that can be monitored, particularly the temperature where we can make out the thing that the cross linking reaction is taking place at that particular temperature. Then oxidative stability, which your environment is oxygen environment only. So, at a high temperature, susceptibility for a particular solid state reaction with oxygen can also be monitored. Then the decomposition behavior, as we have studied earlier also, the decomposition of your oxalate salt, metal oxalate salts, metal ion oxalate salts or the metal ion carbonate salts we can see, even the sulfides. Then in terms of the corresponding medicinal importance or the pharmaceutical industry, it is the purity determination. So, purity determination starting from your sample, which can be useful for pharmaceutical industry like that of your tablet, capsule and all these medicines, to that of your any solid alloy sample or the iron sample or the steel sample. Then one specific quantity we can measure is your specific heat. The specific heat measurement for the sample can also be useful if we look at these particular DSC measurements. So, what we see there, that how we monitor this, that the principle of operation is therefore very important, and this principle of operation will tell us that initially what we can have, a sample is in your hand and which is placed inside a crucible, and then we place the crucible inside the furnace of the instrument, which is definitely now a DSC instrument, which is different from your DTA instrument, along with the reference pan, but the mechanism of keeping the reference as well as the sample pan is same. Then we apply the temperature. So, it is a programmed one because it has some rate of heating process. So, rate of heating process is monotonous with time. It is increasing at a rate of say 2 degree per minute or 5 degree per minute or 10 degree per minute. So, heating can be done in isothermal way. So, isothermal heating or cooling at constant rates we can do in two different ways. So, we can have phase changes. So, the phase changes can be characterized or monitored, and the specific heat of the material can be determined. So, that is the last thing what we just tabulated is the measurement of the specific heat of the sample we can monitor. Then when we give rise to the corresponding energy to the sample or the reference, we are looking for some heat flow. So, heat flow quantities are then we calculate out or calibrated heat flow characteristics of the cell. So, when we get that the heat flow, we can calculate it out based on the corresponding calibration what we have the corresponding cell for the furnace. Cell is your furnace, and how the temperature is going up we can monitor, and how the sample temperature is going up with that particular furnace temperature. So, we can have different types of DSC, and one such is your power compensated DSC. So, one particular technique we will be calling as your power compensated DSC, where we compensate the power which is applied to either sample or the reference, where we keep the power supply thing constant. Like when we study in our next classes onwards, that the electrochemical studies, that we can have some measurements where the temperature, like this temperature, we can fix the corresponding current or we can fix the corresponding voltage. So, similarly here, if we keep the power supply constant, so it can be known as the corresponding power compensated DSC, or the heat flux DSC keeps the heat flux constant. So, these two parameters, either the supply of power or the heat flux what is being received by the sample and the reference, we can keep constant for these two types of measurements. Then what we find, that by observing then the difference in the heat flow. So, when we talk in terms of the corresponding heat flux which is being received, but is not kept constant, only power we kept constant. So, heat flow will be different. So, the heat flow between the sample and the reference. So, what the calorimeters what we have, the calorimeter can measure the corresponding amount of heat absorbed or released during such transitions. So, we can have solid state transformations, and those solid state transformations we can monitor using a calorimeter now by looking at the corresponding amount of heat absorbed or emitted. So, again we are coming back to the same question, that whether we have a exothermic process or a endothermic process, and in that particular situation, so the corresponding position of the chart paper will basically indicate the temperature of a particular type of transition. Transition can take place whether you have a endothermic transition or an exothermic transition, but we should be able to locate the temperature where the process is taking place, and if the process is taking place at a constant power supply mode, we will find the amount of heat being supplied to these two things. So, what we find, that a very important parameter we will be able to find, which is your Tg. So, T small g is a subscript g, this is not your T capital G, is a subscript g. So, we can observe a subtle physical change such as the gas transition temperature, what we use in industrial processes, the quality control instruments, because it has a fix like that of your melting temperature. The melting point, we all know that the purity of a particular sample is known by looking at the constant melting point. Either if you have a impurity in the sample, solid sample, we know that there is be some change in the corresponding melting point. So, that is the depression of the corresponding freezing point and the elevation of the corresponding boiling point, as we know from our school days. So, that particular criteria we can use to fix or we can monitor the corresponding glass transition temperature. So, if we have a fixed glass transition temperature for a particular pure sample, what we can see that is fixed for or can be tagged with that particular sample. So, industrial settings, that means if we go for a typical quality control, the instrument can be used for the quality control. So, a DSC instrument must have to a quality control chemist or a quality control engineer who is looking at the corresponding purity of the sample or any other solid material, such that it can be used for recording its purity and for studying if it is a polymer sample, the polymer curing process. So, polymer curing process is a very important process which can be directly related to the corresponding TG and other parameters. So, TG is very much useful because we are curing this particular polymer sample at this temperature, like what we used to have. That means, we want to eliminate the trapped water molecule to any solid sample. We use this particular temperature as the drying temperature, and that drying temperature we use in some air oven. So, it can also be used to study oxidation, because in air some sample can go for oxidation, and as well as for other types of different chemical reactions. So, these two techniques are therefore very much useful, and the TG occurs when the temperature of an atmosphere amorphous solid is increased. So, where we see that the glass transition may occur as the temperature of an amorphous solid is increased. So, as you have an amorphous solid and at a particular point we see the corresponding inflection, that means a corresponding change in the delta T value, as we have noticed in case of DTA. Similarly, DSC will also record the corresponding temperature TG in this fashion. So, as a step basically in the baseline of the recorded DSC signal. So, when we have the recorded DSC signal, we get a corresponding step like that of your TG plot for your this recording of your TG temperature. This is due to the sample undergoing a change in heat capacity. No formal phase change occurred. So, here we do not have any formal phase change, but the heat capacity is changing at the point of your glass transition. So, as we increase the temperature, we keep on increasing the temperature. What we have started with, the thing that is not a glassy substance, is a amorphous solid, will be less viscous, is less viscous. So, is basically trying to solidifying it at that particular point. At some point then the molecules may obtain enough freedom to for motion to spontaneously arrange themselves into crystalline form. So, if it is less viscous, that means viscosity is decreasing at TG temperature, glass transition temperature. So, you have more freedom of movement of the molecules, and this temperature basically is responsible for the crystallization of the molten species as we grow crystals from the solutions. So, this TC now is useful to monitor the corresponding crystallization process. So, not only the glass transition, we can also monitor the corresponding crystallization temperature. So, what we get? We get the change from the amorphous solid to the crystalline solid, because most of the time when you synthesize some new compound, we know that if it is in the room temperature stirring condition or it is in some high temperature refluxing condition at the boiling point of the solvent, we get, when we cool down the thing at room temperature or when we stop the stirring, we get sometime a crystalline matter or a crystalline solid compound, but in all other cases we get some amorphous solid. But for material of materials of highly important thing, what we get for this rubber like material or the polymer like samples, we get that the crystallinity is important. So, the transition from amorphous to crystalline solid, and there we find a corresponding process, the exothermic process. So, the nature is known and the amount of heat is being they are evolved for this exothermic process is resulting the corresponding peak in the DSC signal, and that DSC signal we can monitor, and that particular DSC signal will be also useful for our measurement, not only knowing the temperature Tc, the crystalline temperature is that temperature which we require for our crystallization, but also the amount of heat is required for that particular transition. So, we can have these two different types of these transitions. One is your endotherm and another is the exotherm. Now, we can separate out, we can differentiate out these two things as one is large, another is small one. So, large well defined endotherms are there. So, for different processes like these, so where we get the large well defined endotherms. So, when we have a pure crystal and that pure crystal is getting undergoing the corresponding melting process. So, pure crystal melting will show large well defined endotherm. Then liquid crystalline material also, that changing one phase to the other phase also will show you the endotherm. Then solvate or the hydrate loss, the solvate, the sample can be solvated or your hydration can be hydrated. So, this hydration, that means the water molecules will go out. So, that will also give you this sort of endotherm. And then stress relaxation of the material, that means material is in one form to the other. The opposite one is a shallow and broad. It was large and well defined, but if you have a shallow and broad endotherm, is due to the moisture loss, is variable also, because it is not a fixed amount of moisture what we are looking for the loss. Then residual solvent or sometimes a monomer is also losing from the polymeric material. Then sublimation process and the melting process is accompanied by showing you the corresponding shallow broad endotherms in the DSC plot. Then we can have the opposite one in terms of the same large and well defined, but endotherms are now exotherms. So, what we find, what we see for these exotherms is now the crystallization, because so far what we have tabulated for the 4 processes over here, another 4 processes are here, nowhere we are seeing the Tc, the crystallization in temperature. So, here also we will see large well defined exotherms. So, the crystallization process is exothermic process and a very large peak area we will get. So, the temperature change or the energy change for this process is also very high, and the crystallization in and from the liquid states. From the liquid state we get some crystals, and that particular crystallization from the liquid state also can be monitored over there. Then we can have the degradation, and that degradation of highly unstable material is also accompanied by this type of exothermic process. Then the rearrangement of the crystal structure, that means rhombic to monoclinic, monoclinic to some other form. So, crystal structure rearrangement can also be accompanied by large well defined exothermic processes. So, the last one will therefore be in our hand as the 4th one, which will be shallow one, but exothermic. So, shallow and broad exothermic processes will be there, which is for a curing reaction. So, the curing reaction what we can take for a polymeric curing of the polymeric sample, or sometime a sample is getting degraded, we want to have some degraded product or we want to have some oxidized form, because sometimes we want to monitor on some oxidized form can also be useful or also have some application for that particular sample. So, we allow it for degradation, we allow the sample also for its oxidation. So, that can be monitored by a very small and which exotherm is a broad one. So, DSC is used widely for examining different polymeric materials to determine their thermal transitions. So, is useful mostly, and in most different cases the DSC is used for the polymeric samples. These melting points and glass transition temperatures of most polymers are available from standard compilations, because the tabulated form or the literature known values we can have in our hand. So, once we make a new polymer or new sample, we have to compare that with the well known values what is there in the standard of these references. And the method can show the polymer degradation by lowering of the expected melting point Tm, for example. So, we can have a new process of making the polymer such that we can have a new parameter, that means the Tm value can be less, such that at this particular thing, that means the process what we have developed, that the process development can also be benefited for your DSC measurements. Then for studies of polymer, it is a handy tool to look at the curing processes, and we see that the cross-linking of polymer molecules that occurs in the curing process is exothermic, resulting in a positive peak, that means the upward peak of the DSC curve, and usually appears soon after the glass transition. So, what we get after the glass transition? So, the cross-linking thing, the temperature we should know, then the glass transition temperature, and where the cross-linking will appear related to that of your glass transition, that we also be able to know from a good DSC plot. Then we have the pharmaceutical industry, they basically look for their studies. The pharmaceutical industry, it is necessary to have a well characterized drug compounds, because the purity is very high and only we are using some amount of milligram level samples. So, these milligram level samples should not have impurity in the microgram level or the nanogram level. So, the purity, it should have a very high purity, and either in order to define the processing parameter, that means how you make the sample. So, we have any pharmaceuticals material or any pharmaceutical compound, we should go through a DSC analysis. So, starting from your quality control to process development in industry, we use this particular and useful technique of your measurement. Then the last one, which is also very important, is the polymorphism, which we can also study by using this particular technique, where a solid can be able to exist in one or more form in the crystal lattice structure, but it can have potentially found different crystalline material, including polymers and metals. So, if they stay in two different crystal lattice form, one is one polyformic form and another is the other polymorphic form, and for this drug material we know that one particular drug material in one polyformic form is active, but the other may not. So, the characterization in terms of their polymorphic nature, we can use this particular technique very nicely for their complete analysis. Okay, thank you very much.